Today we're going to talk about geometric settings. So let's go ahead and take a look at the problems. So a geometric setting is different from a binomial. In a binomial, what happened was we had a fixed number of trials. We knew we were going to do something 10 times. And then we counted the number of successes. So we figured out a probability. What we found out was like there's lots of ways to get 2 successes out of 10 trials, like first and last, first and second. So it was a little more complicated. Geometric is a little more straightforward. With the geometric, what we're doing is we're figuring out the probability of getting our first success on a given trial. So in other words, think about it this way. I wanted to figure out flipping a coin, getting a heads on my on my third trial. So what that means is on the first 2, I missed. I didn't get a heads, I got tails. What's the probability of me getting that heads on the third trial? Well, it's going to be 0.5. I didn't get a heads. 0.5. I didn't get a heads. 0.5. I got a heads. And I multiply those together. So let's take a look at this as an example and determine why things are considered geometric settings. So Mason never has had a pencil when test day rolls around because classmates are tired of having to supply pencils for Mason. Only 15% of the students will give Mason a pencil when asked. Today is the test day and Mason begins asking randomly selected students for a pencil. Let Y equal the number of students Mason asks until he finds someone who will give him a pencil. So the first thing is you ask again that what we're going to do here, it changes slightly. It's not bins, B-I-N-S, it's bits, B-I-T-S. The B, the I, and the S are all for the same thing. T is slightly different. So B is still going to be binary. And we meet binary because he either gets a pencil or not. Independent. Okay, we're going to make the assumption that it's independent because we're going to say that just because one person said no doesn't influence the next person who says no. S, success probability remains the same, like we did in binomial. And in this case, our success probability is 0.15, so our probability is 0.15. So it meets the success probability because what we're going to make the assumption, I's and S kind of go together, that the probability is going to be the same around the classroom. T is trials until first success. So in this case, if we looked at this, he's going to stop after someone gives him a pencil. He's not going to keep asking. So in this case, we actually do meet this because, again, until he finds someone who will give him a pencil. A lot of times you're going to see the word first, but in this case, once someone gives him a pencil, the whole situation's over. So what is the probability that the third person asked is the first person who give him a pencil? So there's that first. So it's saying, what is the probability that when he goes around and asks that third person? So kind of visually, what I want you to see is this. That's saying the first person, the second person, and the third person. So the first person says no. Well, there's an 85% chance that first person said no, because this is someone saying yes. So the probability of someone saying no is going to be 1 minus 0.15, which is 0.85. So the first person says no. The second person says no. The third person says yes. So what we're going to do is we're going to go ahead and, because we're assuming independent events, we multiply those together. Now, I will tell you on your formula sheet, it's there, geometric setting. It says 1 minus p to the x minus 1 and then p. Basically what that is saying is a shorthand way of writing this is this. He is going to get no's 2 times. He's going to get yes that last time. So 2 plus 1 gives me 3, and then those 2 probabilities together. Now, what I want you to realize is the calculator, again, is going to be your friend to answer this. So again, let's just take a look at the calculator. What we're going to do is we're going to go to second vars, and in this case, we're going to go to E and F. Sorry, F and G. F and G. We're going to go to F and G. Sorry, F and G. So what's going to happen is F is an exact number. G is a range of numbers. So F and G. F and G. So in this case, we're going to go to the exact number. So in this case, the probability of success is 15. We want to get the first success on the third trial. So geometric PDF 0.15, 3. And it's saying that that's going to be about a 0.1084. So what's going to happen is we do geometric PDF and we put the numbers in 0.15, comma 3. And what ends up happening is this is our success probability. And this is exactly on third. So that's what we're going to be looking at on this one. And I'll get the answer down there. Okay, so let's go back and actually, again, just make sure we got all that down. Sorry, I had to walk away for a minute. So what we know is that this probability here is going to be 0.1084. So there's a little bit greater than a 10% chance. So in this case, I would not be surprised if he found that first success on his third trial. So the next question says, what's the probability he gets his pencil by the third person? So in this case, what that means is he gets his first pencil on the first person, or he gets it on the second person, or he gets it on the third person. So what that is actually saying is, what is the probability that y is less than or equal to 3? So what that is actually going to do, you actually would need to technically figure out the first probability plus the second probability plus the third probability. So what you need to do is you would need to say, okay, well, nobody says no. One person says yes. Plus we're on the second one. If it's on the second person, the first person says no. The second person says yes. And this third one is what we just did up above. It's at 0.1084. That's the first two people say no. And the last person says yes. That third person says yes. So that's what it is. In the calculator, what you're going to do is you're going to go back to second bars. And we're going to do geometric CDF, 0.15, 3. So the same numbers. So if you notice, we put the same numbers in. But when we do it, it actually is going to add up all of these numbers. So what it's going to do is the geometric CDF of 0.15, comma 3, whereas before it was success probability and exactly on third, 15 is still success probability. And this one is his first success by his third trial. So in this case, the probability that y is less than or equal to 3 is going to be 0.3859. So he's got a little bit less than a 40% chance of getting that first pencil before he talks to his third person. Next, how many people should Mason expect to talk to before getting his first pencil? Okay, so when you see expect mean refers to mean. So we're doing the expected value of a geometric. Here's my expected value of a geometric. It's 1 over p. So it's 1 over p. So in this case, it's 1 over the probability, 0.15, 1 over the probability, 0.15. So we're going to do 1 divided by 0.15. So 6.6666. So 6.6667 people. So on average, you would expect him to have to speak to about 6.6 people on average. Remember, it can't do that, but on average, 6.6 people before he gets his first pencil. Should Mason be surprised if Mason didn't receive a pencil until he asked at least 10 people? So again, if you're saying at least 10 people, what's happening is at least is a greater than or equal to 10. So in this case, I'm sorry, I'm rereading that again. It says, should Mason be surprised if he didn't receive pencil until he asked at least 10 people, So in this case, what we're looking at is we are looking at a probability here of it being greater than or equal to 10. So in this case, we're looking at greater than or equal to 10. So really what I need to do is I need to say 1 minus the probability that he gets it on the ninth person or earlier. So in this case, this is going to be 1 minus geometric CDF of 0.15, comma 9. Again, my success probability. And this is saying by his 9th trial. So again, go back to the calculator. 1 minus second bars, geometric CDF. Going to make it 9. And in this case, I get 0.2316. And in this case, what this is going to say is if we think about that number compared to 5, that's not significant. So again, it's not that unlikely to occur. If you think about it, it's really not that unlikely to occur. So you really shouldn't be surprised because again, we compare that number to 0.05. Since it's greater than 0.05, I'm not surprised. And then the last one is a standard deviation question, standard deviation of a geometric. Again, your formula sheet. There's the formula for standard deviation. The square root of 1 minus p over p. The square root of 1 minus 0.15 over 0.15. It's a plug and chug. Second. Alpha y equals second, get the square root 1 minus 0.15 over 0.15. So that's going to tell me 6.146 people. 1.464 people. So again, this just says there's quite a bit of variability to this. That he's going to need to speak to about 6 people, a little more than 6 people on average to get his first yes on a pencil. But that variability is pretty high. I mean, you could get lucky, you get the first one, or it could take quite a bit to do it. So geometric setting kind of similar in the same sense that we're still doing this kind of BIS thing. It's a little bit more straightforward in the sense that the way you want to think about it is you fail until you get your first success. So I gave you a 12 days of Christmas kind of practice, and it's a mixture of binomials and geometrics. What I suggest is just practice with it, because I'll put the answer key up, but really practice with it so you can kind of see how you can determine which is which.